Okay, welcome to our video for problem 4 from quiz 4. So here we're given a third order differential equation, right? You see at the front we have y triple prime, and we want to solve this differential equation given some initial values. So we have an initial value problem by using the Laplace transform. So, all right, let's get started with it. So first thing we want to do is apply the Laplace transform to the differential equation. So that tells us, right, we have L of y triple prime minus 4y double prime plus 6y prime. And then on the other side, we'll have L of 0. And of course, the Laplace transform of 0 is 0. All right. On the left-hand side, we want to break this up into three pieces. All right. We'll do L of y triple prime, L of y double prime, and L of y prime, pulling the scalars out, because we know that the Laplace transform is linear. So we get L of y triple prime minus 4 times L of y double prime plus 6L of y prime, and that equals 0. So at this point, we need to utilize the fact that we know how to compute the Laplace transform of a derivative. All right, so we need our formula. So we'll start with the most complicated one. So this would be Laplace transform of y triple prime. And this is equal to s cubed times the Laplace of y. And then we have to subtract a bunch of constant multiples of s. So we're going to have minus s squared times y of 0, minus s times y prime of 0, and then minus, well, notice how the s power is decreasing. Now there's no s's, and we get y double prime of 0. All right, so we can take this y triple prime, and we can rewrite now as s cubed times L of y minus, well, let's see, s squared times y of 0. What's our y of 0? It's equal to 1. So this will just be minus s squared. Then we have minus s times y prime of 0, and y prime of 0 is 0. So we won't even get this s term. And then we'll have minus y double prime of 0, and y double prime of 0 is minus 3. So minus 3 is going to be plus 3. All right, so that handled this first Laplace transform. All right, now we need to do minus 4 times, well, now we need the Laplace of y double prime, so we better write down our formula for that. So L of y double prime, right, this is just coming from our table, is s squared L of y. And then again, the s's are going to drop, and we start putting in initial values for y of higher and higher derivatives. Okay, this next one, actually, there's no s's anymore, and we'll just take y prime. Okay, so this L of y double prime is going to become s squared L of y minus sy of 0. Again, y of 0 is 1, so we just get minus s. And then minus y prime of 0, but y prime of 0 is 0. So that's all we need there. All right, next, we're going to do 6 times L of y prime. So, all right, we need L of y prime. Okay, that'll be the easiest of all of these. So that'll be s times L of y minus y of 0. Okay, so, I guess I want that in blue. There we go. So let's see here. We get s L of y. All right, so we're doing this part now. Minus y of 0. Again, y of 0 is 1, so minus 1. And that is going to equal 0. All right, on we go then. So what's our goal? Well, the goal, whenever we're trying to solve these differential equations with the Laplace transform, is to solve for L of the underlying function and then take an inverse Laplace transform. So I have this long, complicated expression, but it's just an expression, and I can manipulate it And so what I want to try to do is solve for L of y. So let's put all the L of y's out in the front. All right, how many do I get? Well, let's see. First, I get s cubed. And then, oh, there's s squared, but you can't forget to distribute. So we have minus 4s squared. And, okay, then we have an s. And, of course, there's 6 of them, so we'll have plus 6s. Cool, and that's all the L of y's we have. All right, now, what about not L of y's, right? Well, we want to put those all on the other side of this equality. So let's see here. We have a negative s squared. We move that over. It becomes a positive s squared. And we have a plus 3, which becomes a minus 3. And we have, well, remember, we got to distribute. So we have negative 4 times negative s is positive 4s. Move it over. It becomes minus 4s. Let's see. Then we have 6 times negative 1. That's negative 6. Move it over. It becomes positive 6. Okay. And so we can simplify the negative 3 and the 6, and we get s squared minus 4s plus 3. All right. So again, we're trying to solve for L of y. So we're going to divide by this cubic, and we get L of y is s squared minus 4s plus 3 over s cubed minus 4s squared plus 6s. Okay, so at this point, we look at our table and we go, yeah, we don't have anything that looks like this. So what do we want to do? Well, we have a cubic on the bottom, and there's an s in every single term. So I can factor that out. Okay, that's not too difficult. So I'll get s times s squared minus 4s plus 6. Right, well, you might think, okay, I could probably do a little partial fraction decomposition. And in fact, on the quiz itself, I gave you the partial fraction decomposition. But let's go through the details, right? A little extra practice here. So one thing I need to know is, am I going to be able to factor this quadratic any further, right? It would be great if I could, because then I could, get a product of linear factors, and the partial fraction decomposition is much easier. Unfortunately, in this case, you won't be able to. And you can check that, right, by looking at the so-called discriminant of the polynomial. If we look at the so-called b term, right, and we do b squared minus 4ac, we're going to get 16 minus 4 times 6 times 1. So 16 minus 24, which is a negative number. That means that this is not going to factor, right? So this is coming, right, from our quadratic formula. All right, x equals minus b plus or minus the square root b squared minus 4ac all over 2a, right? So that's why we care about this b squared minus 4ac. If this is negative, right, then the square root won't exist when you're working over the reals. So, yeah, we check that here. Our b squared minus 4ac is negative 8. So, all right. So we're not going to be able to factor this. So this is going to be an irreducible quadratic, which means if we want to do a partial fraction decomposition, it's going to look like a constant over s, and then we get this irreducible quadratic, and of course we have to use now a linear term on top. Okay, well, let's see. If we multiply through by this denominator, so we're going to multiply through by the denominator, and we'll get that s squared minus 4s plus 3 is equal to a times, well, let's see, when we multiplied through by this denominator, the s's will cancel, and we get s squared minus 4s plus 6 plus, and we have bs plus c times, well, now we're going to cancel the irreducible quadratic, and we just get times s. Cool. Okay, well, we make the observation now that if we make s equal to 0, then the right summand is going to go away, and we'll be able then to solve for a pretty easily. So let's try that, right? Let's make s equal to 0. And again, remember, when we say that, we really mean we're taking the limit as s goes to 0. All right, so when s goes to 0, we're going to get 3 on the left. And then on the right, okay, all the s's go away. You just get 6a. And of course, the right summand goes away. And so a is going to equal 1/2. Fantastic. So we can replace our a with 1/2, and then our a up here with 1/2. Great. Now we need to try to find the b and the c, and there's not going to be a nice s to plug in, so we'll just distribute some things out. So for example, we notice here, how do I get s squared? Well, I can get 1/2 s squared from the first summand, and bs squared from the second summand. And on the left-hand side, I have 1s squared. Right? So 1s squared on the left is equal to, how many s squared? 1/2 plus b. So we know that b plus 1/2 equals 1, and so b must also be 1/2. Okay, so 1/2 can go in here, 1/2 can go up there. All right, now what about c? Well, let's see. C shows up only in this one place, right, where we'll multiply it by s. So we better figure out how many s's we have. On the left, we have -4 s's. On the right-hand side, let's see, we're going to get 1/2 times -4s, so that's -2 s's. So -2, and then we have our c s's. Okay, so -2 plus c is -4, so we conclude c must be -2. Okay, so there we go. We can put in -2 everywhere for c. Fantastic. So we now have a partial fraction decomposition, and so we can rewrite our Laplace transform of y in terms of that. So this tells us that our Laplace transform of y is, I'm just pulling this from up above, 1/2 over s plus 1/2 s minus 2. 1/2 s minus 2 over s squared minus 4s plus 6. Okay. Well, the first term, we're not going to have a problem finding the inverse Laplace transform. The half, just a constant, pull it out, no problem there. You'll just be looking at the inverse Laplace of 1 over s, which we know is 1. All right. This second bit is a little more complicated looking, and it's, again, because of this irreducible quadratic. All right. But when we get that irreducible quadratic situation, the secret, right, is complete that square. So if we complete the square, s squared minus 4s plus 6 is going to equal s minus 2 squared. Now let's see, if we distributed, we get a plus 4, but we need plus 6. So we add an extra 2. All right. So that tells us this bit down here is equal to s minus 2 squared plus 2. All right. Now this is telling us it looks just like one of those either sine or cosine Laplace transforms, right? With a shift. There's just minus 2 in here, but otherwise it looks like it. So remember, the Laplace of sine of at is equal to a over s squared plus a squared. The Laplace of cosine of at is s over s squared plus a squared. All right? So both of these look like s squared plus some constant squared. Okay, that's what I have. Again, there's a shift. We know we can use the shifting theorem, but otherwise this looks just like the denominator in either the Laplace of sine or cosine. The fact that we have an s on top suggests cosine's going to have to get into the game somehow. Right? Maybe we'll have both, but we're for sure going to need a cosine. All right. Now, in order to use the shifting theorem, which I know I need because I'm looking at the bottom, and I see the s minus 2, I need to have an s minus 2 on top. So let's rewrite this so that I do have an s minus 2 on top. Okay, we just cheat. We say, all right, instead of writing s, I'm going to write s minus 2. All right, well, I mean, we're not really allowed to cheat. Okay, if I put in this minus 2, that means I did a half s, and then I also have a half times minus 2, which is giving me an extra half times minus 2, which is an extra half negative 1. So I better put in an extra plus 1. Okay, and then of course I still have my original minus 2. All right, so now this of course will combine to give me a minus 1. And I now have it in the correct form, right? I have my s shifted by -2 here. All right. Now, in order to get it to look like the cosine, I really just want to have the s here, and I actually have this extra constant. So the way I'm going to solve that problem is by just breaking this up into two different fractions. All right. So this second piece, I'm going to well, first there's a plus here, right, in front of the -1, so I can break this up, right? Because, well, we know if you have a plus b over c, that's a over c plus b over c. Okay, so I'm going to take this first piece, move the half out to the front, because I don't want that around, and I'll have s minus 2 over s minus 2 squared plus 2. Then I'll have minus, and I'll put a 1 over s minus 2 squared plus 2. All right, so this second sum end, man, that half is great, because it's just out of the way, and this is exactly in the right form for using the cosine Laplace transform formula along with the first shifting theorem. This last sum end is off by just a little bit, though. All right, I have a 1 in the numerator, but I'm supposed to have a, where in this case, right, I have here down here 2, which is, well, how do I view it as a squared? This 2 is, right, the square root of 2 squared. So I really want to have a square root of 2 on top. Okay, so I cheat. I multiply on the top by the square root of 2. Of course, I'm not really allowed to cheat, and so I also will divide outside here by the square root of 2. And now I'm ready to go. So if I apply the inverse Laplace transform, well, to the left, I'm going to get y. And on the right-hand side, okay, so remember, this is really, we can even pull this 1/2 out to the front. It's a half times the Laplace of 1, right? So the Laplace of 1 was 1 over s. So I get a half times 1, so it's just a half. And then I have a half. Okay, now this is this cosine Laplace transform with a shift. So it'll be the cosine of, well, now what's my a? Well, again, I need to view this 2 as a square, so this will be the square root of 2 times t. Then I need my shift, so e to the 2t. Okay, minus 1 over the square root of 2. And now I have this, I can ignore this 1 now. I have this in the right form as my sine Laplace transform, again with a shift. So I'll get sine of the square root of 2t times e to the 2t. And that is how we solve for y.